Hi, I'm Ned. I've been up here before. I'm a science writer at the Geophysical Institute, and I've been out several times in the field with Carl Tape. He's a real storytelling scientist. But there's a few things you might not know about Carl. Mic drop. One, he was a Rhodes Scholar at Oxford, which is in the UK. He got his PhD at Caltech. He was a postdoc at Harvard, so pretty heavy hitter right here. He's a graduate of Wood River Elementary School. Proud graduate. He's a seismologist who is extremely interested in the ground we're sitting on right now. But he's also a trendsetter in ways that you might not realize. How many of us have posed in front of this sign, nearly naked? Look at this. We've had a lot of opportunity lately, too much this year, maybe. So yeah, it's a Fairbanks thing to do. This one? I'm going to try it. But you know who the first one to do this was? Carl Tape. His father, Walt, took this picture in the 1989 cold snap. Looks like he's enjoying it. Okay, so he's got a great story, and we got to give him all this time. 27 years after this photo was taken, almost exactly, here's Carl Tape.
All right, thanks, Ed. Yeah, once the photo's in the public domain, it's hard to stop. Hey, thanks a lot for being here tonight. The academic title of the talk, the 1912 magnitude 7.2 earthquake in the Denali region of central Alaska. We'll come back to this photo at the very end. It's an honor to be here. I was just thinking, I'm almost positive when I was at West Valley, I was coming to these talks also for extra credit. So it's been a while. It's great to have that continue. I'm going to start with this photo, this image, which is to remind us and those on Zoom that Alaska is a big-time seismic hazard place. This is the latest view of Alaska and the U.S. seismic hazard. You'll note that the scale bar is the same. Okay, that's how big Alaska is relative to the lower 48. You'll also notice that there's a lot of red on Alaska. Red is not good here, generally. Depends on how you look at it. But this is a reminder that we dominate the landscape of earthquakes. We don't have as many people. We're not as in the news as much. But just in terms of how many earthquakes, how big they are, we kind of own it in the country. So this is Alaska. And what it means is in much of Alaska, in the red here, there's a greater than 95% chance within a 100-year period of a damaging earthquake shaking. So that's kind of a reminder of where we are. We are right here in the center of this map. But that's just where we start with. So I'm going to launch into the outline of this talk. There's not too many things. The Denali Fault. Raise your hand if you felt the 2002 earthquake in this room. All right, that's good. And if you weren't even born, that's even better. But we have a lot of people who felt this earthquake. That's where this story is going to start. There's going to be a topic on this paper published 2 years later talking about broken trees in this 1912 earthquake. The heart of the talk is like, what did we learn about this old earthquake? 3 different components and wrap up. So if you're wondering where we are, this is where we're headed. Let's get into it. 2002, we're back 24 years here. But first, we're going to look at a picture of Alaska. Digital elevation model. Here's our great state. We're going to zoom into this region of the Alaska Range, blow it up here. And when you look at this picture of Alaska, your eyes should be drawn to some features. And the opening line in this 1957 paper, a gigantic fault runs through the Alaska Range. Do you think you can see that fault? Maybe. It's a frown. Look for the frown. There's the frown. It's this big arcing thing through the Alaska Range. A gigantic fault runs through the Alaska Range. Just you can see it from whatever scale you can look at, but this is a really good one from space. And here the author names it the Denali Fault because Denali is right next to the fault, highest point in North America. 1 p.m., November 3rd, 2002, magnitude 7.9 earthquake ruptures 340 kilometers in 100 seconds. Those of you, many of you who felt that earthquake, you have a different experience. You were somewhere in a car, in a building, in your house, and you remember the shaking. I'm giving you the academic view, which was it ruptured 340 kilometers from here down to here. How far is that? That's on the Parks Highway from Fairbanks to Talkeetna. That's how long that distance is. An earthquake started in one place, finished in the other place. And it's going in about 100 seconds. So if only you could go that fast, right? That's 7,600 miles an hour. That's how fast the earthquake rupture is. So we're putting some numbers on this earthquake, but the big one is magnitude 7.9 on the Denali Fault. What are some other ways we can convey the size of this earthquake? This is an iconic photograph looking up Black Rapids Glacier off the Richardson Highway. The fault runs right down here. You want to imagine there's a big fault and there's an earthquake rupture coming right at you, okay? Coming down this. This should be white, okay? If you're looking at this photo, it's a glacier. It should be mostly white. It has dislodged chunks of the mountain that have slid across this. This is 1.5 miles wide. You kind of have a different scale here at this, but it's 1.5 miles wide. The earthquake's rupturing through here, shaking the mountains, landslides, just giving you a sense of how big this earthquake is, and it's relevant to the 1912 story in terms of earthquakes in the mountains. Some things went up. This is a few days later. Geologists measuring scarps that were formed during that event, a few meters, trying to document where this thing happened. And most things went side to side. Another iconic picture. We all know, in general, we expect the highway lines to be lined up. This is a spot on the Richardson Highway, and clearly this road is going to be a problem, right? So you've got the highway line here that should be connected here. It's offset in this one spot by 2.5 meters. One shifted to the right relative to the other, and they're surveying that right there. And in the background, we see where this is headed. That's a shot of the pipeline. Here's a view from the air. It really is November 4th. There really was this little snow at that time in this area. This shows the fault rupture. The road's offset permanently. You can see it's offset here. I mean, it's been fixed, obviously, since then. And now you can see what's happening here. We got the pipeline right there on the side. Fortunately, back in 1972, a government-sponsored team of geologists and seismologists had identified this region prior to building the pipeline as having a high seismic hazard. You can find this public report. There's a map in it. Dig into that. It wasn't just seismic. There's permafrost. There's a lot of hazards related to building the pipeline, but one of them was earthquakes. And on that map shows seismically determined segments. This is a really exciting report title called The Final Environmental Impact Statement. Thousands of pages, but here's a cool map in it. And if we look in there, there's this one portion from Denali Dome to Paxson where they assign how big an earthquake you might expect along the pipeline, 5.5, 7.5, and right in here, 8, in this little narrow region, because they know the Denali Fault's going through there. Not really idea about what could have happened in the past, but it's a big fault, it's gigantic, so therefore it might make a big earthquake. That's the idea. So it was known. And because of that, the pipeline was built to accommodate that, to slide on these beams. You'll see them if you look closely in this section. They can slide in and out of the page here on these beams, but they also, you can see how close. In this case, this is a front page of the News Miner. A couple days later, you can see how close this is to falling off. But this is considered a huge engineering accomplishment to say, we thought there might be a big earthquake. We built this pipeline to accommodate large 30-foot type of motion, and there was no major disaster. Meanwhile, I was on the other side of the planet as a student trying to learn seismology, and I was in a lab where everyone was excited about this earthquake. That's what seismologists do. They get excited about earthquakes. But I was sort of like, I'm from there, and there's nothing I could do over there except maybe, just follow along. So when I came home the next summer, after I finished there, I checked out the earthquake effects. That's me, that's 23 years ago, standing on these beams, just get a picture of, this, you can imagine this thing's built to slide in this area. It can slide a couple different directions, but especially laterally in this area. And you wander into the woods, and it's pretty cool. There's trees that are like split apart, as shown here. There's cracks in the ground. You have to imagine if you split wood, especially green wood, it doesn't split very easily, okay? And these trees were just blasted apart. So we took some pictures. My dad and I were down here just checking out the earthquake effects. There's some cabins down there. There's a pipeline. And this is the next summer. And later, a couple years later, as it turns out, these exact trees, I mean literally the exact two trees that I have a photo of, show up in a publication, a scientific study. I thought, well, that's pretty cool. There's an author looking at the fault, looking at these old splits. So where's this story going? These 2002 trees, and there's some older splits. So we're going to launch into the second topic, which is this study about broken trees easing into the 1912 earthquake, motivated by trees that broke in 2002. Here's the paper. That's the title. It's published in 2004, a couple years after the earthquake, of the 2002 earthquake. Something about tree damage during the 1912 Delta River magnitude 7.2 to 7.4 earthquake. Something to do with tree damage and this older event, but also related to 2002. So the study by Gary Carver and others, it focused on damaged trees, which they associated with a known magnitude 7.2 earthquake that occurred in central Alaska, July 7, 1912. We knew it occurred because we had global instruments around the world at the time that could pick up an earthquake of that size. Many people are surprised to know that we had these instruments, over 100 years ago that are good enough to sort of determine about the size and where something is. But the uncertainty on where exactly in Alaska is open. So that's what the study was on, damaged trees. I'm going to pause for a minute just to say, how did we know there was already this earthquake in July of 1912? This is a picture of the actual notepad used by scientist Bino Gutenberg at California Institute of Technology, worked with someone you may have heard of called Richter. And Gutenberg and Richter looked at a lot of earthquakes, but this is the Denali Earthquake. He basically lists the date. These are different stations. You don't need to know the details, but when did the P and the S waves arrive? This is seismology circa 1940s, 50s, trying to understand where this earthquake occurred. And they've got 64 north, 147, or is it 48, crossed it out, get some idea of the uncertainty, and there's a magnitude 7.4. So there was this earthquake that was identified, and the tree damage is being associated with that event. So the idea of this Carver study was to measure some trees that were on the fault, that were damaged in 2002, and then have some control group that are off the fault for comparison, and check if these trees damaged in 2002 had some older damage. We all have some sense that trees carry a really nice record. Annular rings of trees. If a tree's hundreds of years ago, it's telling you something about hundreds of years ago, if you know what you're looking for. So Carver found that some of these 2002 trees had also been damaged around 1912. These are some pictures from the paper. You could saw these trees open, identify some countback rings, 78 years from some tree. You can look at, essentially the short version, he concluded that this pipeline region was the epicenter for this July 7th, 1912 earthquake. And this is a figure from the paper. There's the Richardson Highway. There's the probable 1912 epicenter. And then this other blue line is showing the region of the 2002 earthquake. So we've got the pipeline crossing, Denali Fault crossing right here. That's the prevailing view of this earthquake epicenter. They also compiled a list of observations, mostly from newspapers, across Alaska where the 1912 earthquake was felt, and we call these felt reports. If someone writes it down, describes the shaking, that's a felt report. That's information that is useful to a study like this. One of these observations was from the Parker-Browne expedition to climb Denali. And after coming off the mountain and reaching McGonigal Pass, they described extreme shaking from this earthquake. And their location, talking about Denali, is 250 kilometers, 155 miles from these damaged trees. The expected shaking at this distance from a magnitude 7.2 is just not that extreme. Basically, it would be, we have this intensity scale, but felt indoors by many, outdoors by few. And we'll come back to Parker and Browne, and you'll see that their description was harrowing. It's exciting. And so the mystery setting up this talk is, if we have an epicenter on the Richardson Highway where these trees are damaged, how could such strong shaking be felt 250 kilometers to the west near Denali? And that's kind of where this sat for a couple decades. I'm going to give you a little just insight into why sometimes a scientist like me will pursue a problem. What is it that says why'd you go this route? So I dug into my emails to try to figure this out just for the sake of this. In 2015, so we're back 11 years here, and I wrote to Peter Heusler, who's the USGS chief scientist, geologist, and he just said, hey Carl, it's an enigmatic earthquake. Gary Carver argued it was on the Denali Fault, but one year I showed this tree ring expert the tree. He did some cross dating and it didn't work out to 1912. How is this the case? It's an open question. I look at this paper. I don't study tree rings. I just say, looks like a good story. I assume that's 1912. But someone says, what about that tree ring stuff? Maybe there's some shortcomings there. That kind of got a little more motivated. The next year, I was looking at this, started looking at some of the study. I emailed Gary Carver. I just said, I don't know if you're in email range. I had a question. You listed Fort Yukon on this map, but it doesn't appear on the table. It's just sort of a start to have a conversation, which unfortunately at that time, Gary Carver had retired, was not reachable, but it was just this start to say, maybe I should take a look at this, because I'm from here. I saw some tree damage. I'm really interested in this kind of topic. So in 2016, with some skepticism about the prevailing study and Carver, I started chipping away at this side project. It's kind of a hobby. It really is a hobby. So we're back here to the core of the talk, which is what you learn about this earthquake over this time. So there's three components: eyewitness reports of shaking, seismic recordings from Sitka and beyond, and then there's an aftershock. That's where we're headed. Cut to the chase, this is the compilation of 32 felt reports that we documented in quite a bit of detail, consolidated into 20 dots on the map, kind of for geographic balance. When you look at this map, you might start seeing names of places. Remember, this is 1912. Maybe you'll ask the question, where's Anchorage? Anchorage isn't there yet at this particular time. Maybe the shipping, setting up the railroad, these sort of projects, this is not there. So this is pre-Anchorage, but I definitely put it there. It's the A, just so we know where it is. But you have to kind of bring yourself back in time. What was going on? There were newspapers everywhere. Rampart, Gibbon, this is Fort Gibbon, Tanana, Ruby, Caltag, Nome, Iditarod, Dawson, Eagle, Chicken. These are places we've heard of, but some of them were in their heyday, like Iditarod, for example. So these are places, the number is a shaking intensity that is assigned based on someone's report of this event. So bigger number means stronger shaking, but mainly we're trying to document where was this felt. It should give us an idea roughly of how big it was and even where it was. The pipeline crossing C for Carver is right here. So that's our tree damage site. The Parker-Browne expedition, McGonigal Pass, is right here. So this is the view, and we're going to look at just a couple of these. So there's a story for each of these dots. I don't have the full story, but we're going to look at three of them today: Dome, Fairbanks Creek, and Denali. If we zoom into 1912 Fairbanks, this is where there are 9 felt reports. Agricultural experiment, that's the ag farm. It's been there for a long time. I think 1904. They've been someone taking the weather recording, and that weather person, when they see an earthquake this big, they usually write it down big earthquake. So that's where we have that information. Esther, booming gold, and this whole region is boom town. Like everything in these mining camps out here, Chattanooga, Olness Dome, that's where we're going to be going next. So the next slide is a 1908 map from inside this red box. So it's going to be kind of reoriented, and we'll see what these places are. It's a 1908 map of the Fairbanks mining district. And I always like to think when you see a map of this detail, you say, why did someone make a map so nice in 1908? And the answer may be obvious, but there's a lot of gold coming out of this region. There's a lot of economic boom. There's a lot of use your imagination of what's going on. You need some federal judges, some marshals, some control. But in general, you've got to know, document where people are. This is the Tanana Valley Railroad. So they have a little historic one. Once in a while, they pull out this ancient one, run it at Pioneer Park. But this is where the railroad ran to get gear out to these mining camps, shuttling supplies back into Fairbanks. We've got Hilltop on the Elliott Highway, Olness, Chattanooga. The Steese Highway is just off the map to the south, Pedro Dome. And for those of you ski bums out here, you have a ski land for reference. So this is showing you gold country everywhere you look in this region. This is where a massive amount, biggest gold take out of all of Alaska. And even within a couple years, it will surpass the Klondike in terms of all-time gold productivity. So here we are back, 1908. Earthquake happens this is July 7th, 1912 paper, Fairbanks Sunday Times. Here's the cover of the news. You won't be able to read everything, but we're going to dive into one story. Dome man killed by falling slab. When I first read this, I thought, Dome man, what is that? Like Encino Man, Dome, which dome are we talking about? But Dome was Dome. That is the shadow of Pedro Dome. We'll see where it is. It's on the map. You can see from 1908. Lewis Anderson crushed to death against the face of the drift while at work on 4 above. That's the gold claim on Dome Creek. Body was rescued. So that's the story in the news on this day. So that's a big deal. People dying of an earthquake, especially in the U.S. And it wasn't just a local news story. That's July 7th. This is July 8th in the New York Times, front page. Earthquake shakes Alaska, mine foreman killed. So just to impress, again, it's a big deal. National news, someone dying. This is Dome 2025. Ned and I walked out there with permission from John Reeves, the owner. And what you see out there in the shadow of Pedro Dome, there's tailings, there's some rusted metal, and still mining after 125 years. But when you're out there, I would say imagination wanted. What exactly caused something out here to be on the front page of the New York Times? And so there, thankfully, we have places like photographers to take pictures and people to save them, like libraries and archives. And this is the photo of Dome City in our archives from this era. So this is what a mining camp looks like, pulling out millions of dollars in gold. You can see all these structures in here. You can see little steam. You can see people basically in this valley. This is where they're looking for gold. One of the largest creeks producing, Fairbanks Creek, Cleary, Dome is one of the big ones in the founding of this town. If you zoom into that, you can see just the sort of level of detail in that photo. It's probably a large negative. Just to get an idea, it says Dome Trading, but none of this is there. So a photographer can really bring this to life to think about if shaking hits this kind of town in this area, it helps to both understand the story that's written, but also the intensity of the shaking effect. There's actually a photo of the exact mining claim. 4 above Dome Creek means it's the 4th above the discovery claim on the creek. And this shows an actual, they just happen to have a photo. It's probably staged. You can see the woman there dressed pretty nice, probably not in the trenches. But you also look at this and you say, whatever shaking happened here, I wouldn't want to be there during an earthquake or not during an earthquake. This does not look like a stable working environment. You're talking about blasting permafrost. It was actually 82 degrees Fahrenheit on this day. We know that from the weather reporter. And so you have a probably unstable place, but this is where the spot where the miner died, so far away from the shaking. That's Dome. We're going to shift not too far away to Fairbanks Creek. If we look at the second story on that page, Fairbanks rocked by severe quake. And it says here, at Chattanooga and Olness, the shock was less violent. On Fairbanks Creek, there was a great disturbance. At McLean's store, dishes were tumbled down, stovepipe was shaken, a man sleeping nearby. Bunkhouse was spilled out onto the floor. So that's the story documenting effects of shaking. It's not, the roof isn't collapsing on you, but you could probably place yourself there and there'd be some sense of alarm. So the store was run by A.K. McLean and Dan Egan. It was the hub of Meehan, which was on that 1908 map. It's basically the community hub of Fairbanks Creek. So naturally, trying to understand a little bit about the shaking intensity there from the earthquake, I said, where's Meehan? Where's the store? Who's Dan Egan? We look back at that same map just to orient yourself, again with Ski Land and Pedro Dome for the blueberry pickers. You have Fox here, Steese Highway. There were other stopping points. Gilmore on the map, Golden City. Fairbanks Creek is off to the right. You can still drive down. Still active mining operations, especially beyond the gate there. This is Fairbanks Creek. There's all kinds of structures. The map says Meehan. That's where this community was. Cut to the chase, 2025. This is a photo that Ned took. It's the last surviving structure of Meehan. There is, unlike Dome, there's actually a structure that links us back in time. This is the Egan family kitchen. Happens to be connected to the store owner, the last surviving structure. It's also overlooking Discovery Claim. So this claim on Fairbanks Creek, these are the biggest gold producers. We're talking about the biggest gold production in the state of Alaska of all time in some of these creeks. It depends on sort of which time interval you're talking about. But as we know, Fort Knox is not far from here. This place has been producing gold since this era. So in 2025, I was given a tour of Meehan by Eric Olson, who I learned was the great-grandson of Dan Egan. That's pretty interesting. Fourth generation. Eric owns a cabin on Fairbanks Creek. I'm talking about a store that, just curious where we could find out, and he pulls out some old photos. One of these photos is from 1948, which shows the kitchen, the building that's standing, and at that time, this is the store. The store is right next to that structure. So if we know where this structure is, and we know that this is the store, we know where this store was during the shaking. We can pinpoint exactly where the shaking effect was. So that's very interesting. It's still 1948. I kind of like to see what it looked like further back in time. So we stand there, take a picture from this summer, looking out at this view. There's the cabin. I'm looking down Main Street or whatever I can imagine here. But this is where, again, like we saw it at Dome, imagination is wanted. You can sort of close your eyes, read a book, but we don't have any videos of the Gold Rush era and what's going on. The best we could hope for is a photograph. So looking at this view, this is not from archives. This is just from the family generation passing down. There's a photo. And that really brings to life the kinds of places. This is what, in this era, what this mining camp looks like, not far from Ski Land. This is what Fairbanks Creek looked like, and there's a terrific shot of the store. And why this matters is, again, when you can assess what kind of damage might happen, it's a good idea to understand what structure you're talking about. I would not want to be in that structure during an earthquake. I would not, the cabins maybe, but in general, you can see what kind of shaking effects. When you look at this photograph, you can actually read on the side, if you zoom it in, it says Egan and Griffin. That's Dan Egan. Fairbanks Creek, at this time, they've got vehicles. When they first came down there, they're running horses. That's the store. So we've identified to within a few meters where this shaking effect that's actually kind of significant to the story about the earthquake is. Who's Dan Egan? How can you not appreciate a photo like this? Finally, we got the center of the character here. This is the guy. This is the store owner, Dan Egan, 1908. Just take a close look at this photo. You've got the axe, you've got some fur, you've got a gold pan, you've got a pistol. obviously posed at some level, but this is 1908 on Fairbanks Creek, photo that's in the family. I just took a photo of a printed photo to show that. And to me, this character, Dan Egan, he's the one, he owns the store that we found that was damaged in the 1912 earthquake. But to others in Fairbanks, Dan was grandpa or great-grandpa, as I learned. And one of these people turns out to be one of my coworkers. I'll just put the photo up there. If you don't see a resemblance between these two, that's Dan Egan, 1908. That's Kelly Egan. She's a triplet. She's got a brother named Dan as well. Are here. Thanks to the Egans. I should raise a hand to all the Egan descendants here. But so we've got a connection, a very personal connection between these characters in the story. For me, I'm just trying to understand this earthquake, but as it turns out, my coworker is an Egan, and that's kind of a cool connection. So continue along with this story. We're going to go southward and upward. So we're going from Fairbanks down to Denali. Back a few days, June 29th, 1912, 20,200 feet elevation on Denali. That's where we are here. That's where our story goes. And at that elevation was the highest anyone had ever reached on Denali, someone who was 660 feet from the summit. This is a photograph taken in 1942 to recreate exactly where Belmore Brown was at the moment in a blizzard he decided to turn back, spending his whole life trying to get to the top of this mountain. After crawling on his hands and knees away from his partners, he's like, I'm going for it. On his hands and knees, as far as his exhausted muscles will allow him to go, he stopped and realized, I'm not going to be able to find my way back. I'm going to die on this mountain. And thankfully, he decided to turn around because we have their story to tell from that. So I think this photo is taken from the summit. That's 660 feet away. You think, come on, surely you could do that. But then if you really read the stories and you realize they've been on snow for 35 days straight, eating canned whatever, they're not doing well. So that's the moment there, June 29th. They're going to hustle down at that point. Obviously a little disappointed, but they said, we got to turn around. So on the morning of July 5th, after traveling day and night, we reached Glacier Pass. For the first time in 30 days, our feet rested on warm, firm ground, and never as long as I live will I forget the joy of it. At 10 p.m., the earthquake struck. I just said, firm ground, no more. So we're going to see their story. You don't have to read this. I'm going to give you some highlights, but it's one of the most verbose, impressive accounts of earthquake shaking that you'll read. It was published in Outing magazines, published in the book that they wrote. But basically, they're standing there on the grass at this pass. They're off the mountain, essentially, and they hear a deep rumbling from the Alaska Range. The valley above us turned white. The earth began to heave and roll. I forgot everything but the desire to stay upright. There's a boulder turned loose, broke loose from the earth. Then came the crash of our falling caches, followed by another muffled crash as the front of our hill slid into the creek. The stove had overturned in their tent. A great flat rock, which we used as the base for the stove, had moved. This is strong shaking. This is strong shaking. So this is sort of like you're outside, you don't have anything to fall on you, but you're still worried about what's coming. They turn around, they say, look at Brooks. So they're only something like 8 kilometers away. They can see Mount Brooks, namesake of Brooks Building next door. And the whole extent of the wall that formed its buttress was avalanching. I've never seen such a sight of overpowering grandeur. The avalanche seemed to stretch along the range a distance of several miles like a huge wave. Like a huge wave, it seemed poised for an instant before it plunged downward into the ice fields. A great white cloud began to rise. It billowed upward, 2,000, 3,000, 4,000 feet, hung like a wall. The great wave of avalanche debris came rushing down our valley. At this point, they're heading for whatever remains of their tent, which has much of their stuff has been thrown around. They got inside as this basically cloud of ice debris just blasted through them. So that's their story. Avalanches of the Alaska Range, strong shaking, stove turning, rocks moving, can't stand on their feet. So we asked the question, okay, is there any other evidence for these avalanches? Enter the 1913 Stuck Carson's expedition. This was the first successful ascent of Denali. And if you read their story in the book, The Ascent of Denali, published the next year, now just before leaving Fairbanks, we received a copy of a magazine article containing the account of the Parker-Brown climb, and in the narrative, Brown speaks of this northeast ridge as a steep but practicable snow slope. The actual quote was a very steep but climbable pitch. Well, we get the point. And points to a photograph. They look at this photograph, professional mountaineers at the time, and they say, we got this. We got this ridge. That looks climbable. They did it. We're going to do it. Looks like a good route. We'll follow it up. To our surprise, this is what they found. The ridge offered no resemblance whatsoever to the photograph, the 1912 photograph. And they conclude through a long text that there could be no doubt that the earthquake had disrupted the ridge. The ridge that the pioneers of 1910 went up in one march, that the Parker-Brown surmounted in a few days, relaying their camping stuff and supplies, occupied us for 3 weeks, while we hewed a staircase 3 miles long in the shattered ice. So we can't say for 100% that ice fell in 1912, but it's in the 99% range. You got professional climbers looking at photographs from one year to the next saying, there's no way this is just regular erosion of a mountain. So the ice shattered, this avalanches that were witnessed disrupted this climbing route, and we have strong evidence that this was part of the shaking in that earthquake. Back to the Parker-Brown expedition. They're trying to get out. They're on foot. Denali, June 29th, Carson's Ridge, McGonigal Pass. They're going north. Kantishna, 3 days later, Glacier Creek, Tolovana. And Tolovana on the Tanana River, that's the end point. Because Tolovana, how many of you been down the Tanana River to the Tolovana Roadhouse? Have you ever seen there? There's 10 people or so. It's still there. That was on the telegraph line in 1912, meaning if you got to that point, your story's going global. So you've got to get to that point, or your story's going nowhere. And that happened on July 23rd. So we'll see how this timeline fits in. This is the step here. Denali, Carson's Ridge, McGonigal Pass, Kantishna, Glacier Creek. They're trekking on foot to get out of, basically end their trip, get on a boat, and float out the Yukon and back to the lower 48 eventually. So that's the picture. If we look at the stop, July 13th, they visit Fanny Mackenzie or Quigley on Glacier Creek, famous pioneering woman who just, if you go to the national park or Kantishna, you'll hear about her. If you look at the diary entry from Belmar Brown, it's in the Dartmouth archives, July 13th, earthquakes have been working steadily. The big shake was not as bad down this way as it was on the Clearwater. So we learn about aftershocks, and we learn that it wasn't quite as strong in this area. Both of those things are relevant. If you're in the epicentral region, you're feeling aftershocks. If you're not in the epicentral region, you're probably not feeling aftershocks. So they make it to Tolovana, and that's why our timeline is now 17 days after the earthquake. The expedition reaches Tolovana, news breaks in Fairbanks. Parker fails to scale Mount McKinley. The same earthquake that killed the Dome Man and shook McLean's store also shook these climbers. And the end of the article talks about the earthquake. The professors of the opinion that they might not have escaped with their lives had the shock come while they were on the mountain. I fully agree with that. After the end of our story and knowing where the earthquake is, that is an understatement even by news standards. That story was also big. New York Times, same published date, July 24th, 1912. Big story covering the whole page. Go close to the top of Mount McKinley. Essentially, this story is they did not quite make it. It was so close, didn't make it. The earthquake doesn't fit into that main narrative, but the next day, even in the New York Times, July 25th, you've got the story right here. McKinley climbers back, and in that excerpt, they say right here, you can see felt earthquake. They mention this earthquake. The one that we knew about happened 17 days earlier. It's just the news connecting the climbers to that hadn't been broken yet. So the witnesses from Dome Creek, Fairbanks Creek, Parker-Brown are among 32 felt reports. I hope you get an idea that it's a dot and it's a number on the map, but there's merit into sort of understanding the story, trying to connect it to the time period, but also getting a better idea of what that shaking intensity means. So we look at a dot like this, and now we've learned something about 2 of the episodes in Fairbanks. This is McGonigal Pass. We've got all these other stories to fill in this information. From these reports, we can get basic rules from other parts of the world with shaking intensities and earthquakes, and we can use that to get an idea of where the earthquake was. And if you took just those felt reports and these numbers, you would put an epicenter right here at this arrow. So it's right, the uncertainty, you might say, well, it's somewhere around this area. It's a star, but there's some fudging in terms of the numbers and the assignment, so I would say the uncertainty is sort of this larger region. But it's pretty far over here from where the Richardson Highway is right here, the prevailing view of this epicenter. We're now going to go to the second part, seismic data. And on the second section here, we're going to look at recordings from Sitka and beyond. This will be shorter, but you'll see how important it is. Sitka was the only station in Alaska. It was actually set up, and Russians had a station there monitoring the magnetic field, which was really important for a number of reasons. And at some point in 1904, they decided to put a seismometer in there. This shows what someone in Sitka is looking at little wiggles on their seismometer and says, whenever that gets big, they're going to write down when. They're going to have a clock that's pretty accurate. They're going to write down the hours, minutes, and seconds, and how big the shaking was on the paper. You can imagine someone is assigned this job, and they're just writing down what happened, and that's one of sort of like about 100 places around the world doing this. So just an aside, if you happen to be saying, was this earthquake in July 6th or July 7th? Which one is it? If you're catching that, please, there's 2 different times. We got local time, which is kind of relevant to the news, but seismology is going to be using a universal time. So the earthquake occurred locally, July 6, 1912, 10 p.m., and that is July 7th, 1912, 8 a.m. UTC. It's basically like London time is the standard there. So just an aside. This is a map looking straight down on Alaska. It's kind of a weird map, polar looking, but it's the way a seismologist would look at the world. The degrees say, like, how many degrees away are you from the epicenter here that we determined? All of these arrows is somewhere an instrument in 1912 that recorded this earthquake, and we used that information to try to locate the earthquake, just like we would today, only our methods today are obviously way faster, way better. But we had in 1912 coverage that's pretty impressive. A lot from Europe, North America, Japan, and this is the information that in our study we carefully revisited and collected all this information to determine this epicenter. The one on the left is for P waves. The second arrival is the S waves. Both of that information gets used to say, where was the earthquake based on far away seismic data that has nothing to do with felt reports or newspapers? And that's where the earthquake is. So taking far away information, we determine that this is the epicenter. The data tell you this is where the earthquake happened based on that information. This is the epicenter, this is the uncertainty region, and this is, just to orient ourselves, this is the Parks Highway, the Richardson Highway, the trees are over here. And so here we have this instrumental epicenter, a few kilometers away from the 7, which is the Parker Brown eyewitness account. So lo and behold, it's pretty close to the one that we got from felt reports. So from felt reports, said this earthquake is here. From the instrumental data, said it's here. This is just showing the sort of zoom in using the felt reports. We basically have this region, but uncertainty-wise, the whole region is available. It's also close to McGonigal Pass, where Parker and Brown were. And it's really far from the pipeline. It's far away, so we've got all these different lines of evidence, which we'll wrap up soon. So this is the picture looking at, to put it all sort of in one picture, we have the 2002 earthquake, ruptured 340 kilometers in this blue line. This is the Richardson Highway, the tree damage, the pipeline. Our story is shifted over here. Denali, that's Denali. This is the instrumental epicenter of where this earthquake was in 1912. There's one last point about the aftershock. And 38 hours later, there's an aftershock, as we now know. And I'm going to show that story because I think it's one last really dagger for this evidence. This is the Sitka Station register. A lot of numbers in there. From June to December 1912, every earthquake recorded in Sitka. We don't know necessarily whether this earthquake that recorded, was it right next door? Was it on the other side of the planet? That's why we need a lot of different observations to determine things like where an earthquake is and how large it was. So if we look at the Sitka register, here's the main shock earthquake, 5 centimeters of motion that was recorded. It's kind of a lot. It's the most that happened in that 6-month period. That's the main shock earthquake. And if you look at this register, there's a few other ones that are kind of big. And if they were in the same point, there's a question of what are these? Can we say anything about aftershocks? Are they all aftershocks? If we dig in here, we can find this earthquake. They actually list that it was felt right in Sitka. This is just a local earthquake nearby that had a big recording. This one turned out to be a magnitude 7 earthquake near Kodiak. We know that one because it was globally recorded. So the question was, is this an aftershock? It's 38 hours later. Is this an aftershock? If so, where was it? Maybe it was at the pipeline. So in 2024, I asked the International Seismological Center, do you have any arrival time data for this earthquake on July 8th? There's no record of this. It's sort of below. It's not big enough to be globally identified and cataloged. So I said, can you help? I'll wait as long as you want. I said, I've been waiting a long time. And I'd like to get a complete story here. So you tell me if you can pull it. So a few months later, we got their compilation, did the same thing, take the arrival times, totally independent data, ask the question, arrival times, where's this earthquake? And this is where it is. So it's a different earthquake. It's 11 kilometers away. So at that point, 2 different data sets, 38 hours later, it's a magnitude 6.4 earthquake. This is absolutely an aftershock. And its location itself helps even further support the location of the main shock. You've got 38 hours apart, a magnitude 7.2, 6.4, essentially on top of each other. That helps further provide this evidence of where this main shock occurred. Again, I keep coming back here. This is where the pipeline is and the tree damage. So surely the Parker-Brown expedition felt this earthquake, right? They just spent 3 or 4 pages describing the main shock. They felt a 6.4 in the same region, right? I mean, they've got to. I've got the diary. Here it is, July 8th, leaving from McKinley Fork. Pause. Arrived McKinley Fork. Okay, sledded about 150 pounds of sled and packed dogs, saw a big cow moose on the Clearwater. Right in there at noon, there was a 6.4 earthquake. I'm going to just infer, based on the fact that they said their waist was 23.5 inches, also in their diary, when they got into Kantishna, that they were thinking about food. Because they are experienced an earthquake of the size that they saw, there was unquestionably, they felt this earthquake. And they said later, we felt them. But anyway, just showing you, I was a little disappointed. For all the richness that Belmore Brown gave, I thought, man, if you could have just mentioned that. So when we submitted the manuscript, we basically said, we found no felt reports for this aftershock, which occurred at local noontime. There's no preserved newspapers. For some reason, those 2 pages on July 9th and 10th are gone. Belmore Brown doesn't mention any earthquake in his diary entry. Lacking felt reports, we only know about this from newly collected and analyzed instrumental data. That's generally good enough for me. I mean, I believe the seismic data. This story is locked in there. But then I remembered this meticulous merchant from Knik named Orville Herning. There's a lot of Hernings also in Alaska, including one on my soccer team who I coach. And he had written daily diary entries from 1898 to 1947. Just ponder that. I can't, every day for that long. And as it turns out, his diary is right here at Rasmussen Library. This is the kind of stuff we have in the library. You can just sink it in, get used to reading old cursive. This is July 6th, July 7th, July 8th. Orville Herning said, I'm going to change my pen color at this moment because this event was a big deal. About 10 p.m., heavy earthquake vibration lasted for 5 minutes. Log buildings cracked under the shake. That's the main shock. That's not actually what excited me the most about this entry. It's 2 days later. He gives you the time. He's right to within 2 minutes on that entry. It's 10 p.m. within 2 minutes. It's that one on July 8th. He says, at noon, another quake. So that is the only known felt report for the magnitude 6.4 aftershock. So while the manuscript's in revision, I was like, wow, cool. So it was felt. At least one human wrote it down, and we've got that evidence to really lock in that I believe in instrumental data, but I definitely believe this merchant. So back to we're winding down here, bringing into the epicentral region to say, where was this earthquake? What evidence do we have that it's in the Denali region? There's 4 things. There's the globally recorded seismic data, puts it right here with this kind of uncertainty ellipse shown here. We've got felt reports from all across Alaska, put it down here, but even larger uncertainty. It's in the region of this plot at least. Pipeline's way off to the right there. We've got the Parker-Brown account from McGonigal Pass, super strong shaking, avalanches of Mount Brooks, Carson's Ridge collapse that the Stuck-Carson expedition encountered, and we have finally the aftershock 11 kilometers. So 4 very strong lines of evidence to tell us this earthquake is in the Denali region. So that's one mystery solved. This earthquake in 1912 occurred in the Denali region, not in the Delta River Valley on the Richardson Highway. What's interesting is that also opens up some other new mysteries, which is, well, there's one, what damaged those trees? I'm not going to dive into that here, but something damaged these trees. It was not this earthquake. The other question, though, more interesting, is which fault hosted the 1912 earthquake? Just because it's in the region, what does that put? What does that tell us? And there's also the question of when and where is the next major earthquake in the region, and how does 2002 and 1912 sort of impact that discussion? So the hosts for the 1912 earthquakes, we're looking in this region. I'm going to throw 2 out there. The first one could be the Denali Fault. That's that gigantic fault that runs through the Alaska Range. It ruptured in 2002. That's definitely a possibility. They were basically standing on it when they felt the earthquake. The other option, though, is this McLeod Creek thrust fault. In the last 20 years, including work coming out of UAF, identified that there are these thrust faults that are kind of convergent and one thing thrusting up over the other. And that is a very different kind of fault, but that is right within this region and a candidate for what could have been at play in this earthquake. I come back to the title slide, which is shown here. Does anything catch your eye in this picture as being possibly odd? I don't know. Not me, I'm not a geologist really. It's this thing right here. That thing's a little odd. It's like a little ledge. That's a scarp of an earthquake, an ancient earthquake, and that's the thrust fault. What you're looking at is the north peak of Denali. The Denali Fault right here is actually just behind, it's 6 kilometers away, so they're very close, this thrust fault and the Denali Fault, and both of these are major players that could create large earthquakes. So we have this Denali, McLeod Creek thrust fault. I can't tell you exactly where this is. I just told you it's 250 kilometers away from where we previously thought it was. But we're at least looking in the right region, looking at what might be the right faults for thinking about this kind of activity. I'm wrapping up here just to say that the full story academic version is shown here. Just came out February 2026. You're hearing the story for the first time. And these are my co-authors on that, including even a terrific librarian here that helped with this story. So check that out if you're interested. I want to finish too with the thanks to the co-authors, funding, those who collected the instrumental data, saved the data, fault maps, archivists. Thank you for helping with Fairbanks history. A lot of the Egan descendants, people for land access, GI Public Information Office, and most of all, I don't have anything to talk about without someone to listen, so I really appreciate your support for everything that makes culture in Fairbanks, science, sports, arts, everything. Thanks for being here.
Thanks, Carl. What a sign-off. All right. I think Rod Boyce is going to come down and help me with the mics. We'll take questions from our in-room audience first, so just raise your hand, and Rod or I will bring you a mic.
Okay if you have to leave, but stick around if you can.
I'm just curious, is there a possibility that both faults had an earthquake? I mean, does one trip another one? I'm just curious on that.
Yes, and the short answer is we have to look no further than the 2002 earthquake, which started as a previously unknown Susitna Glacier thrust fault, 7.2 earthquake just on that section of the fault. The question is, why did you turn into a 7.9? That's one of the biggest questions in seismology. When an earthquake starts, you have no idea how big it's going to be. I don't even know if it knows how big it's going to be. But it started as a thrust fault, not on the Denali fault, and it absolutely triggered, directly led to a 300-kilometer rupture. So it's a terrific analog to say, absolutely, we could have both going. And in the paper, we say, here's one fault, here's the other. Both could easily have been at play. And for those of you from other parts, you might be thinking like San Andreas, southern San Joaquin Valley. That's a place where the San Andreas bends and you have a thrust fault. You could very well have many of these situations where you have overall strike slip motion, but you could have a nearby thrust fault that would really change the size and shaking and where it's extent. Great question.
So any chance that some of those old records are of sufficient quality to get a focal mechanism?
Oh, John Davies, Seismolab founder from the 1980s, Board of Regents extraordinaire. Thank you for that question. Yes, after I published the paper, I basically said, this study I've been chipping away at for a while, just the arrival time information. And what Dr. Davies is getting at is that there are real seismograms out there, like wiggles that look like this, beautifully recorded records of ground motion that people use to pick those times. And if we use that information, what more can we say about this event? And the short version is, I guess I approached this problem to say, I'm going to completely tackle two parts of this problem. And after that, it becomes too overwhelming for me. There are data out there, and after I published this study, people sent me from Cleveland. I have beautiful seismograms from this earthquake. I have beautiful seismograms, but if I were to start that problem, I'd probably send dozens to hundreds of emails to make sure I had every last recorded piece of paper archived, and it's just probably not going to happen in my lifetime. But the point is there's other information that could be used to get that information, and we allude to that. I hope to inspire someone. At the end of the paper, it says, go find some seismograms. There's more to be done, but for us, it was just like, let's figure out where this earthquake was first.
Thanks for the talk, Carl. It was really fun. I have two questions. Did you ever get in touch with Gary Carver again? And then also, can you talk a little bit about your process, like how you first came up with or how you first got into it, and then, how you started getting co-authors?
So Gary Carver, I finally got a home phone number. He lives in Kodiak. He's kind of a legend in this field. I got on the phone with him and sort of ascertained that he was not doing very well. And he passed away, I think, a year or two ago. But he wasn't in the sort of science discussion mode. And so I talked with his closest collaborators. But by that point, if you follow someone's study really closely, you can start to see a little bit about how they approached the problem, what their strengths were, what their weaknesses were, and start to expose some of those. And without Gary Carver's study, we would have eventually gotten here, but it probably might have taken another 10 years. So it's one of those things where it's like, I'm so grateful that he pursued that, but it also took me a while to like sort of question it. And that's what was happening 10 years ago. And the thing, honestly, that put me over the edge on finishing this study was a librarian here. And I said, I am not in position, I cannot justify going into the microfilm archive and rolling out these tapes and figuring out how to scan. And I just said, maybe I'll just request interlibrary loan. Can you send me a newspaper? Because that's a lot of work. You have to go get a reel, scan it, and this angel of a librarian did it. And then I kind of abused that request relentlessly. and said, we've gotten so much out. So it was sort of, it's an odd thing of how it finally finished, but in that process, we got the data set together and everything just sort of aligned. Most of the time in science, the more you look, the more scattered things get and the worse your story is. Some of the biggest stories are people with very limited amounts of data. You have a tiny amount of data, you can tell any story you want. The more data you get, oftentimes it starts to be contradictory. And so in this case, it's like, oh my gosh, everything lined up here, which is why I was kind of excited to share like a success story rather than like all these pieces not working out. But at that point, I was like, this absolutely, to everything that I know, this earthquake's in this region. And sorry, the process is, as I said, it's a hobby. So I'm doing this, I did have some funding for some 6-month period in the last 10 years, but it's mostly just like chipping away and being very patient, knowing that eventually this story will come together and probably no one else is gonna be able to sort of like scoop you on that. Yeah.
Hey, thanks for being here. Was there some kind of international entity that most seismologists were kind of all formulated with when you showed the global map of all the different places? And if so, how long was it taking someone here in the United States to get the data from across the world?
I think any scientist would be well served to think back to the question you're asking, which is like, how did this all work? And I will tell you, it's a massive, if you look at magnetic field observations, it's a huge geopolitical thing as well. So you have entities, you have seismic stations in northern Italy or Austria that over the time periods here are going from regime to regime to regime. I mean, you have seismic stations trying to operate during times where borders are changing. And so in this time, it takes someone to recognize the global advantage, the necessity of having all the global data to really selflessly put themselves out there and collect it. And that happened to be in the early 1900s. That was basically a guy named Turner in England who collected relentlessly all this information from all over the world. It took months and months to collect these arrival times, tried to put them in standard formats, and then share them with everyone else. Guy died in 1913, World War I started, and the whole thing ended. So basically, yeah, you're right to point out it would be very, very hard. That's what I do. I say, International Seismological Center, can you please try to comb everything in paper and give me a digital file? And that took them, because they're not paid to do that either, that took several months to just come up with that. So information's out there, but it's hard to preserve it.
Hi, Carl. Thanks for your talk. One thing that occurred to me is how good is the timing for all these international stations in 1912?
Yeah. Fortunately, so these arrival times, we assume uncertainties of sort of 30 to 60 seconds, which sounds like, depending on who you are, that sounds pretty low, actually. I mean, when we run the estimation, we have ways to assign uncertainties for each clock of each station. But I believe the origin time and the end with enough data, our origin time, we know when this earthquake started to within 10 seconds. And just to tie this to another story, the origin of seismology opportunity is that in 1944, when the Trinity test was detonated, the Gutenberg, the person I showed there, asked the people who detonated that first nuclear bomb and said, when did you detonate that? And they said, we tell you, but we don't know within 30 seconds. And Gutenberg told them to within 2 seconds. And that was a turning point in the field of seismology, because as soon as they realized that a seismologist just standing out there looking at data could determine the location and size and timing of a nuclear bomb, enter the Cold War and enter seismology, really growth period.
And about Gutenberg, and Gutenberg and Richter did publish an epicenter for that earthquake.
Yes.
Was that shown?
It is. It's one of the things, I had too many things on this map. This is Gutenberg Richter.
Okay, yeah, I kind of remembered it being over towards,
There have been some studies that put things over here, but yeah, that's. But when you look at the guy's notes, you're like, are you throwing dart on the map? Because, you know, it was at 147, he crosses it out. So that's kind of, with this old stuff, you get a sense of like what the uncertainty is. It's not just a typed out number, it's someone, it's literally a sketch pad. Looks a little sketchy, but this is by far the greatest seismologist of the 20th century. And so it wasn't that far off, but people believe that. When a great scientist says this is where the earthquake is, it takes a while to overrule that person.
Okay, we're going to move to some online comments and questions. I'm sure Carl will be happy to have in-person folks swarm him once we're wrapped up here if you have more questions. So we have lots of people joining online.
Okay to leave again.
Okay.
Thank you very much.
People from all over Alaska, Homer, Willow, Denali Park, Glacier View, Talkeetna, Eagle River. Also in the U.S., or the lower 48, we're in the U.S. too. Washington, California, Michigan, Nevada, Tennessee, and someone joining from Japan. So I'm not even sure what time it is in Japan right now. So one quick comment, which I think is just very, very sweet. Sue Sheriff on Zoom says, Carl, one of your childhood librarians from Nome Library is so pleased at the light you are shining on libraries and librarians. So that's about the cutest thing I've ever seen.
It's a treasure over there. I mean,
It really
Rasmussen's
is.
world class.
And then I think we have time for just one question, but I can get these other ones to you, Carl. There was a comment in the Zoom chat that the Katmai eruption also occurred in 1912. I'm curious, too, if you think there's any correlation between that eruption in June 1912 and the July 6 earthquake.
Our paper that we published has an entire appendix devoted to the confusion caused by that eruption. Because, first of all, this climbing expedition, they're going up, they've been on the road, they start in Seward. They're going overland. They're trying to make this as hard as possible. They're making their tea, and ash is falling out of the sky. They're that far away from Katmai, ash is falling out into their pot. They don't really realize they heard the eruption from a long distance. It was heard in Fairbanks, the Katmai eruption. It's the largest eruption of the 20th century. And where am I going with this? What was the question? Oh, the Katmai, yeah. So what happened was Katmai happened, and that was heard, and it also produced magnitude 6 earthquakes, 14 of them. And so the news is just a slow news cycles, especially getting in and out of regions like Katmai. Even now could take a while, but I guess there's bear cameras. But anyway, back then it takes a while for news. So people were totally confused. And when they first said this earthquake happened, they just said it's probably Katmai. And there's a lot of confusion over those. But the short answer is no way. There's no connection between the volcanic eruption of Katmai and this earthquake. I'm not, again, you'd have to work to connect those. But there was definitely a connection in the news and a lot of confusion. And this expedition had both of them. It's like June 6th, they're on the mountain, ash is falling out. They come off the mountain and they just get rocked by this earthquake.
I have a real quick question. Maybe you mentioned this. Is your recently published paper open source, and how can people find it if they want to read more?
Yeah, fortunately, it's free. You can, if you Google any, I don't know, Carl Tape 1912, you'd probably hit it. But yeah, I think you could find it with the title at least.
Okay, great. One more round of applause for Carl. Thank you, Carl.